Hello everyone, and welcome to the first exercise solution. In this tutorial I will talk about the math refreshers sheet. Before I start, I wanted to highlight that you should interpret this sheet as a kind of test to see whether your mathematical abilities are adequate for this lecture. In the past we had a lot of students who struggled with the content and especially at the exam realized that this actually is a math-heavy course. So if you feel unprepared, if you feel this is too much for you, please do a preparatory course first and try to fresh up your linear algebra, calculus, and probability theory. While the first topics in this lecture might seem to be easy, it will become a lot more difficult later on. And machine learning is a lot about mathematics, so you should really hone those skills. Okay, so now let's start with the exercise sheet. In this sheet, we start rather slowly. The first problem is mostly about very basic linear algebra. So let me get some more space here. Okay, so the question is, what are the dimensions of these shapes, of the matrices especially? Because sometimes people struggle with these basic properties. So we are given that x is m-dimensional, y is n-dimensional, and z is p by q dimensional. So first of all, we look at A. Okay, so A is right multiplied with y. So that means that it has to be n-dimensional on the right-hand side. Right? So let me get okay, so n-dimensional on the right-hand side, and on the left-hand side it's x transposed, so that's m by n. Okay, this is rather easy, so I'll make it a little quick. So b is multiplied with x by the right-hand side, nothing by the left, so left has to be 1. Scalar should be the result here, and then the right-hand side should be m. Okay, let's do this correctly. Okay. So now C left-hand side is y, so that's n, and then right-hand side is z, so that's p. Okay. D, right-hand side is nothing, left-hand side is z, so that's q by 1. E, left and right-hand side are y. We've got the transposed here, but that doesn't change anything because it's just y everywhere, so that's n by n. And then f is only returned as f, so this has to be a scalar. So that's 1 by 1, if you want to do like a matrix notation of this, which is completely unnecessary, but we can still do it. Okay, next up, problem 2. So we have x is a vector, m is a square matrix, and we have this function which is given in some notation. We want to express it via matrix vector notations. This is to practice a little bit how to do matrix vector notation, because this is very useful and we will use it very often. And we've seen people in the past trip out on this rather simple part. Okay, so we have f of x. I'll do these arrows from now on, just for you to, because it makes it easier to read. Okay, so we have sum over I, sum over j. I'll leave out the limits because it's not really necessary. xi, xj, mij. Okay, so we can rewrite this. We can pull out the xi because the right-hand sum doesn't depend on it. And then we can say, okay, this is the sum mij, xj. Because those are scalars, we can swap them around. So that's what I did here, and then it becomes clear that this is just a matrix vector multiplication. So this is just m times x, mi. Okay. Come on. Move. I don't want you. So mi and column. So this is now a column vector. And this on the left-hand side is again in this time around a vector matrix, not matrix vector multiplication. So this is the same as saying x transposed mx. Right? Okay, so what usually helps to think about here is basically think about the dimensionalities, like we did in the first exercise, right? So this is like a 1 by n matrix, this is an n by n matrix, and this is an n by 1 matrix. Basically, these shapes always have to fit. So that's what you practiced in the first exercise. Well, this is not readable. N by... Oops. Okay. Okay, so third problem. We're interested in solving the following system of linear equations for x. A times x equals b. Under what conditions does the system of linear equations have a unique solution x for any choice of b? Okay. So here we can consider a couple of cases. What we basically want here, if this has a unique solution, then A would be invertible, right? I mean, we can directly see this. So basically say if A invertible, then we can say A times x equals b is equivalent to x equals A inverse b. Right? Let's actually make this a bit faster. Okay. So, right. Okay, so next up we can think about, okay, A has to be invertible. So what other cases are there? So first of all, if A is invertible, that would mean that A has full rank, right? I mean, we can also say A has full rank. So what other cases are there? So A invertible also means that A is a square matrix. So A square. So what other cases are there? So otherwise, if m smaller n, oops. I mean, this is equivalent to looking at the rank, right? So it would be equivalent to saying, hey, the rank is smaller. Then the solution is not always unique. Solution not unique. The other case is n smaller m. Oh, let's actually make this consistent. M greater n. Then there are cases where the solution simply doesn't exist. So solution not always exists. And this second case can also happen if A doesn't have full rank. Okay, so next up, B. Assume that m equals n equals 5, so we have a square matrix, that's good, and that A has the following eigenvalues, -5, 0, 1, 1, 3. Does equation 1 have a unique solution x for any choice of B? Justify your answer. Okay, So we need to justify, we don't need to prove here. So we have a 0 eigenvalue. And earlier we said, hey, A has to be invertible. But being invertible or being full rank means that you have no 0 eigenvalues. You only have non-zero eigenvalues. Therefore, it does not have a unique solution. So basically, we know that A invertible is equivalent to only non-zero eigenvalues. So the answer is no. So this is a justification, right? Only saying no would have not been enough. Okay, problem 4. Assume that there exists a matrix B such that B times A equals A times B equals I. What can you say about the eigenvalues of A? Justify your answer. Okay, let's see. If B times A equals A times B equals the unit matrix, that means by definition B is the inverse of A. This is exactly how you define the inverse. So A times B equals I means that B equals A to the minus 1. And we know, so there exists an inverse, and we know if it's invertible, it has to have only non-zero eigenvalues. So therefore, A only has non-zero eigenvalues. And that's it. Okay, problem 5. The symmetric matrix A is positive semi-definite if and only if for any x it holds that xTAx greater or equal to 0. Prove that a symmetric matrix A is PSD if and only if it has no negative eigenvalues. PSD will become important later on when we talk about kernels. And in general, it's an important property to have in various different cases. So let's see. Here we start with the definition. I mean, first of all, we need to consider we want to prove an if and only if relation. So we need to prove it both ways. So let's start with the no negative eigenvalues case. So no negative eigenvalues leads to A is PSD. So we start with this direction. Okay. So whenever we have a set of eigenvectors, so eigenvalues, non-negative, so we choose the associated eigenvectors, we can always make them orthonormal. So we choose orthonormal. Okay, only eigenvectors. What does orthonormal mean? Orthonormal means that Vi, so the inner product of Vi and Vj, equals delta ij. So this is a Kronecker symbol, and that means 1 if I equals j and 0 otherwise. Okay, so they're normalized, that's why there's a 1, and they're orthogonal, that's why there's a 0 here. Okay, now a set of orthonormal eigenvectors is a basis. So it spans the full n-dimensional space, and therefore we can express any x by a combination of these eigenvectors. So we can express x as x equals sum over I, sum wi, vi. So vi are our eigenvectors, right? Oh, did it automatically? What's going on here? So these are the eigenvectors. Okay, now we go back to the definition. So we look at x, a, x. So actually this is transposed here. Okay. And with that, we can express this via the eigenvectors, right? So we say, okay, this is the same as sum over I, wi, vi. So that's the left one. A, sum over j, wj, vj. That's the right one. Actually, there's a transposed here. Okay. And then, okay, we can change this a little to make this more beautiful, because those are so we can move the scalars to the left, because those are just scalars. A, vj. Now we know that vj is an eigenvector, and therefore we can just say, hey, this is the same as just the eigenvalue. So lambda j vj. Right? Now, this is transposed here. Now we can pull out the eigenvalue, and then we see, hey, we multiply these two. But they're orthonormal, right? So the result of this is just a Kronecker. Okay? So we rewrite this as, oops, sum wi, wj, lambda j, delta ij. A bit more space. Zoop. Okay. And then looking at that here, we can say the delta here basically means that one of the sums goes away. That's a property of the delta. It's also valid for integrals, but the delta function is a bit, well, it's still simple, but the mathematical side of it is a bit more involved. So what we can say is that the sum over j goes away, and we're only left with wi squared lambda I. So always having a delta basically just means you can set one of the indices to the other index. And wi squared, this has to be larger or equal 0, right? Because it's squared. And then we know that the eigenvalues are non-negative. So this is greater or equal 0. So then we know that the whole thing together is also greater or equal 0. That's the first part. Now to the second part. So the second part is the opposite direction. A is PSD, implies no negative eigenvalues. So now we just say we have some eigenvalue and eigenvector. Lambda and v eigenvalue of A. Okay, so now we use the fact that A is PSD, and we look at the eigenvectors. So we have 0 is smaller equal V transposed A V. So directly look at the eigenvectors. And this is true because A is PSD. Now, because these are eigenvectors, we know that this is the same as lambda V, right? And then we can say, hey, okay, we can pull out the lambda, and then we just have lambda times the norm of V. So this is greater equal 0. And the left-hand side says, hey, the whole thing is greater equal 0, so therefore lambda has to be greater equal 0. And that is it. Okay. Problem 6. Let A element are m by n. Prove that the matrix B equals A transposed A is positive semi-definite for any choice of A. Okay, so we go back to the definition. X transposed B X. That's what we are interested in. So that's the same as X transposed A transposed A X. Now we can say, hey, we summarize this left-hand side, we put it into a parenthesis. So we say AX transposed AX. Right? But now if you look at this dot product here, that's just a norm. That's a squared norm. AX 2 squared. And what do we know about the norm? It's non-negative. So this is greater equal 0. And therefore, PSD. Done. Okay, now we move on to calculus. So again, we start with a simple problem. So we only have a scalar. Later on, so the next problem, we'll do basically the same thing, but with multivariate calculus. So in higher dimensions, not just scalars. Okay, so under what condition does this optimization problem have 1, a unique solution, 2, infinitely many solutions, or 3, no solution? Justify your answer. So if you look at this problem, it's just a parabola, right? It's not symmetric because it has this linear term as well. So that's like f of x. So when does it have a unique solution? Well, if there is a minimum, right? So when does it have a minimum? So that's if a greater equal 0. Two, infinitely many solutions. So this is the case if it's completely flat. When is it completely flat? If a equals b equals 0. And 3, when does it have no solution? Well, either if the parabola looks down, or we have a linear function, but it's not flat, it's tilted to some way, because then the minimum would go to infinity. So basically, either this case or this case. Right? So that's like if a smaller 0 or a equals 0 and b not equal 0. So that's essentially all the cases we don't have yet, right? So we've covered the greater 0, we have the equal 0 and b equals 0. So now this part of this is left, and that's what we have here. And then a smaller 0 is also covered. Okay, now I've just reasoned about parabolas, right? But we can make this more thorough by looking at the derivatives. So let's do that, because we will need that later on. So basically the first derivative, f of x, is just ax plus b. And then the second derivative is a. So when do we have a minimum? So let's separate this a little. So we have a minimum. So this is completely general, right? This might not be a global minimum, but it is a minimum. So we have a minimum if f of x equals 0, and if f second derivative, so the first one was the first derivative, second derivative is greater than 0. Right, so the greater 0 means that it's upward bending, and the equal 0 means that it's flat. You can make further statements like this and say, hey, if the second derivative is 0, then you have a saddle point, and if it's smaller than 0, it's a maximum. If the first derivative is 0, of course. Okay, next up. Assume that the optimization problem has a unique solution. Write down the closed form expression for x star that minimizes the objective function, i.e. find x star equals argmin f of x. I mean, we've basically solved this by writing down the derivative, so this will be very quick. Okay, so we know that f prime of x equals 0 equals a times x plus b, or like prime of x star, so at the minimum. This is equivalent to x star equals minus b divided by a. Okay, so those are the simple cases. Now we'll go to multivariate calculus, where things become a bit more difficult, but it's also way more relevant. Like, you rarely have a scalar in practice, so this is what usually happens. But the thing is, we still have a nice function here, right? So it's still just a quadratic function, which is basically the prime example of a convex function. Okay, so again, we consider the following function. Here we have a quadratic part, a linear part, and an offset. A is symmetric, P is D. We are interested in solving the following optimization problem, the minimum. Compute the Hessian of the objective function. Under what conditions does this optimization problem have a unique solution? Okay, so let's compute the Hessian. To get the Hessian, what we need to do is we need to calculate all the elements. So what we do is basically we look at, let's actually make this more explicit, d by dx L, I think I used L in the solution, yeah. d by dx k of g of x. Okay, so now we write down g of x. If you have set some properties in your head, you can actually do all of this in vector notation. I'll go like the pedestrian way and just solve it with the sum form, because I don't have all the equations in my head. And this is more safe. Like, it's slower, but you can be sure that everything is all right with this. Okay, so here we'll use I and j, sum over I, sum over j, xi, aij, xj. So this is just g of x written down, plus sum over I, bi, xi, plus c. Okay, and now we take the derivative with respect to k. So the first part still here, And then, okay, 1/2 sum over I, sum over j. Well, essentially, I don't need j anymore, because we know that if j is not equal k, or like I and j is not equal k, then this will be 0, right? So that's like a delta function. We can do this intermediate step, but I'll just skip it. So what we have then is we have aik xi plus 1/2. So that's basically with respect to the second one. And we eliminated the sum over j. And now we can eliminate the sum over I with the delta function. So here we have sum over j, aik, oops, ajk, sorry. Let me write this again. akj xj plus bk. Right here we don't have two x's, so we can just only b remains and c goes away. Now what we can do is we can say, hey, aik, a is symmetric, so we can just write this as aki. Right? And then we see, hey, these two sums are the same, so we don't need to write it down twice. Okay, so we can write down d by dx L of the sum over I aki xi plus bk. And now the derivative is quite easy. We basically do the same as previously, and we just say, okay, this is AKL. And it's symmetric, so that's the same as ALK. Let me actually put this into a new line. Oop. What's going on? Let's reduce this. Okay. And so now we only have like the elements. So let's write this down in like a more beautiful form. So the Hessian of g of x equals a. Okay. And then the second question is, under what conditions does this have a unique solution? So a unique minimum, we have a unique minimum if A is PSD. Like, first of all, unique minimum if the Hessian equals A is positive definite. Sorry, I said PSD earlier, but actually it has to be positive definite. Because if it's semi-definite, basically you have some direction where the curvature is 0. So there is some vector where the curvature is 0. So if it's positive semi-definite but not positive definite. And then you don't have a unique solution, but you have like a set of solutions along this direction, right? We'll see that a similar argument in point B, so I'll not write it down. Right. Okay, some small addition to this. What is the Hessian if it's not symmetric? The symmetry just makes the whole thing easier, because if it's not symmetric, we can basically not do this step here, right? We cannot switch the indices here, and then we have to handle the left-hand side different from the right-hand side. And then what happens is that we see these two again in the solution. So then we have 1/2 A plus A transposed, which is just the symmetric part of the matrix, which is interesting, right? Anyway, so that was a side note. Okay, next up. Why is it necessary for matrix A to be PSD for the optimization problem to be well defined? What happens if A has a negative eigenvalue? Okay. So let's do this properly. And prove this. So basically what we want to prove is A PSD, so well defined. Now we'll use a little trick. Oh, sorry. The other way around. So it's necessary. A has to be PSD if it's well defined. So this is the other way around. The other thing would be it's necessary to be well defined if it's PSD, which is not the case. So the way we prove this is by switching this order, by saying A is not PSD. So if it's not PSD, then it can't be well defined. Not well defined. By the way, what does it mean to be well defined? Well, it means that there should be some solution. If there is no solution, it's not well defined. Okay. So if A is not PSD, A not PSD, so that means that A has a negative eigenvalue, right? Because if it had only non-negative eigenvalues, we've proven that, it would be PSD. So let's look at this eigenvector. The associated eigenvector. Let's call it V. So then what we have actually, let's say V is normalized, and then also use, okay, V doesn't have to be normalized, but let's also use A as scalar. So basically we look at the direction defined by V, and just look at the point along that direction, right? So that's just some scalar. Okay, now we look at the quadratic term. So that's, if we move far away from 0, the quadratic term is always dominating. So we look at A, V transposed, A, V. So that's plus O of A. So this O of A basically just says, hey, that term, so those are smaller terms that grow equally fast or slower than the norm of A, while the quadratic term obviously grows with A. But let's define this precisely this O, because some people haven't heard of that. So if a function f is in O of some other function g, that means that for all c greater 0, there exists a x0 greater 0, so that for all, that's not, what is this? That for all x greater x0, it holds that the absolute value of f is smaller or equal than c times the absolute value of g. So it basically means that f grows at most as fast as g. So if you move towards infinity, it behaves like g. Or like, it is not stronger than g. Let's say it like this. So by using this up here, we basically say, okay, we've got some terms that are less than quadratic. This is a very useful notation. So here we can say, okay, we have a squared, a times v, that's v is the eigenvector, so that becomes the eigenvalue. So that's v transposed v, let's actually put the lambda in between here, lambda v, plus again some terms that are not as important. So now if you look at this, it's like a squared lambda and then the norm. So this basically means that, I mean, this is a very thorough argument for the simple fact that we have like a negative curvature in this direction. But anyway, this is good if it's thorough. So as we take a to infinity, this will decrease always, because this is smaller than 0. This is greater equal 0, and this is greater equal 0. So in total, this is smaller than 0, right? And then as we increase a, the whole thing will decrease. And therefore it doesn't have a minimum, no minimum. And therefore not well defined. Okay. Next point. Assume that the matrix A is positive definite. Write down the closed form expression for x star that minimizes the objective function, i.e. find x star equals argmin of g of x. This is a very important question. I mean, we've done the same thing for a scalar earlier, but usually in machine learning you don't have scalars, you have vectors. And usually in machine learning you're interested in minimizing the loss function. So usually what the problem boils down to is exactly this. Usually you don't look at it with respect to x, but with respect to your weights w. But you need to solve this. In most cases you can't directly solve it because your problem is non-convex. So you can only do something that approaches the solution. But in some cases you can, and in most cases this is the problem formulation. Okay, so in our case we can. So let's look at this. Again, we look at the gradient. So like in problem 7, we just say, hey, let's look at the gradient. So the first derivative, d of x, we've already solved that, so I'll not go through all the details again. So this is akj xj plus bk. So this is in index notation. Now if we look at the full thing, I mean, if you don't know, this is the gradient. So the gradient is just a times x plus b. Now we know if we're at the minimum, the gradient is 0. So minimum ax star plus b equals 0. So this is equivalent. We just solve for x. X star equals minus a to the minus 1 b. Great. We know that we can do this because, or actually not this, but this. Because a is positive definite. So that means that the eigenvalues, I mean actually this is equivalent, eigenvalues greater 0, strictly greater, and this leads to a invertible, because we have no 0 eigenvalues. And therefore we can directly solve this. Okay, so that's problem 8. Problem 9. Okay, now we move on to probability theory. We have a couple of basic statements here. You don't really need calculus here, it's just mostly a couple of tricks in probability theory, like linearity of expectation, using the variance, etc. Okay, but first off we have two statements. Basically problem 9 is conditional independence implies independence, and then problem 10 is independence implies conditional independence. And for those of you who remember some probability theory, you will know that those are both wrong. So what is the approach if something is wrong? Usually we find a counterexample. Oops. So let's do that. Let's find a counterexample. Some space here. Even more space. Okay. So this is basically conditional independence implies independence. Question mark. Question mark because, well, it's not wrong. It's not true. Let me actually move this, because this is getting really hot. I hope Camtasia won't freak out. Okay, so we know it is false, so we disprove by counterexample. And we want a rather descriptive counterexample, so let's construct one. Okay, we imagine a coin. We don't know if it's fair or unfair. So it can be either fair or unfair. This is denoted by the random variable C. Okay, what is a fair coin? Well, a fair coin basically means that the probability of a coin flip being tails equals 0.5. And an unfair coin means that the probability of a coin flip equals tails is, let's go to the extreme, let's say equals 1. Okay. So next, okay, we have these two different kinds of coins. So what's the probability of getting each one? So we say the probability of getting a fair coin is the same as the probability of getting an unfair one. So it is 0.5. I'll do commas here because they're easier to read. So this means fair, and this means unfair. I mean, you could also call it biased. But yeah, I'll call it unfair. Anyway, so we do coin tosses. Coin tosses. Two coin tosses, A and B. Coin tosses are independent. That's like basic property of coin tosses. Independent. So they have the property that P of a coin toss, given that we know what kind of coin it is the same as P of the coin toss, given that we know what the first coin toss is and we know the coin, right? If you throw it twice, the probability will always stay the same. Okay, but this is only if you know the coin, right? So for a fixed coin, you know the coin, it's the same. But now, what happens if you don't know the coin? And you want to calculate the full probability of getting heads or getting tails from start to end, essentially. So this is if C is known, C unknown. Okay. So we can derive this. P of A equals tails equals P of A equals tails. Okay, so first off we use the sum rule. So P of A equals tails and C equals fair plus P of A equals tails and C equals unfair. So this is the sum rule. Sum rule. And then that is the same as P of A equals tails, given that C equals fair times the probability of C equals fair, plus the same thing on the other side. Oops, can't write anymore. A equals tails, given C equals unfair, P of C equals unfair. And this is the product rule. So these are two basic rules of probability theory. Very useful, very often. Okay. Now this is 3/4. if we plug in all the numbers. Okay. Now let's do the other side. What if we now want to know P of A equals true, given that equals tails, given that the first coin toss is true, tails. So here we basically switch up the product rule. So we divide by the P of B. So P of B equals true, goes into the lower part, and then we have this up here. Okay, and then we can do the same stuff again. Okay, P equals T. So then we can separate out C and then do all these calculations. You have that in the solution sheet. I'll not do all the small steps now. So let's say ... equals 5/8 divided by 3/4 equals 5/6. And thus P of A equals T is not equal P of A equals T, given that P equals T. And therefore we've disproven it. So it's like, I don't know. A working counterexample. Okay, next part, problem 10. So here we want to look into independence implies conditional independence. So we look at the other way. And as I said earlier, as people might know, this is not true. Let's actually write this down here as well. Okay. So here our counterexample is way more simple. So we just look at two dice rolls. They're independent. So we have two dice rolls, A and B. And we have another variable which sums them up. C equals A plus B. So an easy example of this is if you play Settlers, for example, or any other board games with two six-sided dice. You usually sum them up. So here we say, hey, what if you rolled C equals 3? So that's usually a very bad roll. Now we're interested in, okay, what is the probability of that the first die is 1? So that's B, sorry. Well, what are the combinations here? It's like either 1 and 2 or 2 and 1. So the probability of this one being 1 is 1/2. Okay? And now we say, hey, what if we condition this on the other row? So what is the probability of this being 1, given that C equals 3, and we know that B equals 2? Well, there's only one possibility here. A has to be 1. Otherwise it wouldn't sum up to 3, right? So the probability is 1. But we know that the dice rolls are independent. So here they're independent which is equivalent to saying P of A given B equals P of A. And now we have that P of A given C is not equal to P of A given B and C. So we've proven it. This is actually more interesting than it seems, this fact. Because you can basically make two independent variables dependent by using another variable. This phenomenon is commonly known as the Burksen's paradox. Another example of this would be if you have a university and you admit students, and like in the US, you have students are either admitted via their sportsmanship or via academic excellence, like they have good grades. Now, if you know that someone is admitted, you don't know why they are admitted, right? So now you have like 50-50 chance. However, for the reason. However, if you know that they are very fit and they are an excellent swimmer, then the probability of them also being excellent in mathematics or like very intelligent becomes lower, even though a priori you would say these two are independent. This pops up in various cases, and in machine learning it's called the explaining away effect. Because by knowing that someone is a good sportsman, you explain away their admission to university. So you explain away the other variable. Okay. Problem 11. You're given the joint PDF, so we have a probability density function. Therefore, we already know those are continuous variables, not discrete, of 3 continuous random variables. Show how the following expressions can be obtained using the rules of probability. So this is very basic. It's just like you should know these, how to obtain this. So first off, P of A, we get this by marginalizing out B and C. So basically P of A, B and C. So we just integrate over B and C. That's called marginalizing out. P of C given A and B, that's 2. We get this as earlier, by just dividing, by using the product rule. So that's P of A, B, C divided by P of A and B. And then how do we get P of A and B? Well, again, by marginalizing out. So that's P of A, B, C. My pen doesn't like me anymore. Divided by P of A, B, C, D, C. 3. P of B given C. Again, this is just like a combination of stuff. So first off, we say, okay, this is P of B and C divided by P of C. Just again the product rule, and now we again marginalize out. So these are just different combinations of the product and the sum rule. So the sum rule for continuous variables is integration, not summation. So the upper side we get by P of A, B, C, dA, and the lower half we get by 2 integrals, P of A, B, C, dA, and dB. Okay, that's it. Problem 12. Researchers have developed a test which determines whether a person has a rare disease. The test is fairly reliable. If a person is sick, the test will be positive with 95% probability. If a person is healthy, the test will be negative with 95% probability. So that 1,000th of the population have this rare disease. Actually, it's not rare if it's 1 in 1,000. That's already rather common, I would say. A person chosen uniformly at random from the population takes the test and obtains a positive result. What's the probability of that the person has the disease? This is like a standard question for the Bayes theorem, right? So you probably have seen this in your probability theory class. Okay, so let's denote disease by D and the test by T. So we want the probability of having the disease given the test. So this is the test, and this is disease. So the test positive, and then this is like has disease. So the probability of this is P of T given D times P of D divided by P of T. I mean, either you just know the Bayes theorem, or you, from the previous exercise, you can also derive this easily, right? So you can say P of D and T, that's the upper side divided by P of T, and then, okay, we can split this up via the product rule again, and then we obtain this. Good, now we can just split up the lower one using the sum rule and the product rule with stuff we know. I'll not do this now, and then the end result is that the probability is 0.019. So that's very low. That's actually the interesting thing about the Bayes theorem. Like, even if you have a very accurate test, if the probability of having the disease is low, it's not enough. Like, the probability will still be extremely low. People have actually used this argument to say, hey, with the coronavirus, the PCR tests are not accurate. Like, we don't have as many cases as we test because, hey, Bayes theorem, like, there's a probability of this going wrong. Problem with this is PCR is extremely accurate. There are actually countries who have done hundreds of thousands of tests and have not had a single disease. So calculating this probability there is like, the probability, like, it's so reliable that it almost never has false positives. So yeah, that argument doesn't hold. Like, it's way too simplistic for this case. So don't trust that. Also, like, if you have, oh, I can make this negative, nice. Now this is like a first test. So you can actually test if you have a false positive by doing another test and then another test, etc. And if those tests are independent, this will shrink exponentially. Or like, this will increase exponentially. Like, the probability of not having the disease given the test will shrink. Okay. So problems 13 and 14 are now concerned with Gaussian variables. So 13 is a univariate Gaussian and 14 is a multivariate Gaussian. Actually, for these, you don't really need to know anything about Gaussians. It's mostly just about the variance and the expectation and some linear algebra tricks. But that's often the case with Gaussians. Like, you don't really need to remember the density function for the Gaussian. You should know that it's like e to the minus x squared and then some stuff, but that's all. Okay, anyway, let's look at this. We want the expectation of f of x. So expectation of f of x. Let's expand this. Expectation of ax plus bx squared plus c. Now, we know that the expectation is linear, so by the property of the linearity of expectation. My pen gets worse and worse. Nobody can read this. Let's try it again. Linearity. That's better. Okay. We can split this up, so that's expectation of x plus b times the expectation of x squared plus c. Okay, expectation of x is just the mean. So that's mu. Right, let's actually write this up separately. So the mean mu is the expectation of x, and the variance sigma squared. Sigma is the standard deviation, sigma squared is the variance, is expectation of x squared minus the expectation of x squared. Okay? So by knowing this, we also know that, hey, if we have e of x squared, this is equal to sigma squared plus e of x squared, which is just sigma squared minus the mean squared. Right? So therefore, e of f of x. Let's actually make this green, if it works. Yep. Ah, come on. What's going on here? I mean, I know what's going on. My computer is overheating and therefore it doesn't like doing stuff anymore. Okay. Oh, it's like really hot there for the CPU throttles, and then it becomes slow. Anyway, so the expectation of f of x equals a times mu, so that's the first term, plus b times sigma squared minus mu, or like plus mu actually, oops. Plus mu squared plus c. Okay, so now let's do this with multivariate Gaussians. The expectation, so let's start simple, expectation of g of x. Equals the expectation of a times x. Okay, and now linearity, so we have a times the expectation of x, and that is just a times mu. And done. Okay, next one. E of g of x transposed. Let's see. So that's the expectation of ax, xta, t. So now again, linearity of expectation. Let's write like lin, where we use the linearity. So that's a times the expectation of x transposed. Let's go back to using these arrows. times A transposed. And then regarding this stuff, we can again use the variance. So here our variance is defined as E of x transposed. Well, like actually variance, yeah, it's actually the covariance matrix. It's not just the variance. And it's defined rather similarly. Just need to be aware where the transposes are. Actually, let's write down, this is the covariance matrix. Covariance matrix. Good. So now that we know this part, we know that this equals A times, so again we can do the same trick, because this is mu transposed, right? So we can say this is sigma plus mu transposed A. And that's the reason for this. Okay, so next step, again, it's a bit more difficult. The expectation of g of x transposed g of x. This is equal to, so let's insert, oops, not this, x transposed, A transposed, A x transposed, no, not transposed, AX. Okay, so what do we do now? The A's are on the inside, so we can't use linearity of expectation. But we can use a little trick. This is often useful in linear algebra, because the result of this is a scalar, right? If we take the trace of a scalar, it is still the same scalar. So we say, hey, this is the same as the trace of x transposed AX. So the reason for this is trace of scalar equals scalar. So if you're not familiar with the trace of a matrix, let's call it, I don't know, M, it's basically the sum of its diagonal. So sum over I, MII. Now if you have a scalar, obviously you only have one here, so that's always the same. The nice thing about the trace, though, is the trace is invariant under cyclic permutations. So that's what we're going to use now. So that's equal to the expectation of the trace of, so we cycle this periodically, which gives us AX transposed A transposed. Nice. Now the A is on the outside. So the reason for this is that the trace is invariant under cyclic permutation. which is a very useful property. But what does it mean? It means that the trace of ABC equals the trace of CAB equals the trace of BCA. So basically cycle this through, right? So this basically, that goes there. That's how the permutation works. Okay, next trick. The trace, we know the trace is just a sum. And we know that E is linear, so E has linearity. And therefore we can just exchange the two. So this is the same as the trace of the expectation of AX, X transposed, A transposed. And now this is familiar, right? We solved this just 10 minutes ago, up here. So we know that we know that this is the same as the trace of A times that's an ugly sigma. Sigma plus mu transposed A transposed. So that's the transposed missing here. Okay, and that's it. Okay, now last question. What's the covariance of g of x? Now, since we've answered all the other questions, this is pretty easy. So, oh, this looks like a minus. Let's make it a dot. So this means that E of g of x transposed. So the covariance is defined. I mean, we just had this, right? Covariance matrix up there. Minus E of g of x E of g of x transposed. So we've solved all the parts, we just need to find them. So this is g transposed, so that's what we did here, right? Wait, not here, that's g transpose g, that's what we did here. So that's A times sigma plus mu transposed times A transposed. Come on. Transposed. There we go. Minus expectation of g of x is just A times mu. So we know that this is A times mu t at. Right, we have the second one, the transposed one. Now we can simplify this further. We can say, okay, A sigma at, so let's just multiply out the parenthesis here, plus A mu transposed at minus A mu transposed at. Hey, we've got the same thing twice. So we can remove this, like so. And then what we're left with is A sigma A transposed. Okay, and that's it for today. So what have we seen? We've done some repetition, some basic repetition on linear algebra first. Oops, That's what we started with. Let's go up here. So this was fairly easy. And we basically repeated some basic stuff there. And then it went a bit harder. Here you had to know some things about the properties of matrices. Then we did a little proof on PSD, because PSD is often important. And proof techniques here with the eigenvalues, that's a good thing to be able to. And then we went to calculus, like some basic quadratic functions. First a scalar one, then a multidimensional one. And these basically are prototypes of machine learning problems that you will see very soon. Like linear regression is already like this. And then we did some probability theory with 2 counterexamples and then a couple of basic probability properties that we tested. Some of these questions are harder than others, as you probably have seen if you've solved this. I would say the hardest questions, like, I don't know, part 3 of this here. So part 3, that's this. I wouldn't quite see that you solved this from the get-go, but you should have solved most of these questions without much issue, especially after having freshed up your skills with the stuff we've mentioned, with the materials we've mentioned. Again, if you found this really hard, this course will not be fun for you, because that's kind of the style we will continue with. Anyway, thank you for watching the solution. I hope it was helpful. And next exercise solution will be by someone else, so we'll see each other later in the semester. Bye.